Okay, have a nice weekend. You doing?
No.
Okay. Let's stay a few minutes.
Okay.
Did you switch off the mic? Here, switch it off. You don't need it.
All right. Can everyone hear me? Hello? Can everyone in the back hear me? Yes? Perfect. Okay, so I'm going to be introducing a couple of techniques that are very helpful. Because we're using the student edition of Patran, there are actually some limits. You actually have to pay to have those limits removed. Like, the school pays for SolidWorks. So you can have several million elements if you want. But with this, we're limited to what? I think 5,000 nodes. But that's not too much of an issue for this class at all. So one technique is, I don't think it was discussed earlier, is the seed meshes, the mesh seeds. So once you have your structure, it doesn't matter whether you import it from SolidWorks or you design it within Patran. Once you've got your structure and you have your materials, the next step would be you can apply your loading conditions, but I'd suggest first you create your mesh, and then I'm going to show you why. So when you end up wanting to create your mesh, you're going to go to Create, or first go up to the Meshing tab, and then you're going to get this little bar here, go to Action Create, and then we want the mesh seed. So basically what this does is it allows us to control how dense we want our mesh to be in certain areas and less so in others. And this is extremely important if you end up having any type of curves or any surface that you think is going to be a stress concentrator or a stress concentration point. So one method is, a convenient method is the uniform. So with this, you can define how many mesh seeds you want on a specific surface. So eventually, we're going to be applying some type of force on the top surface. So let's have more there. So let's say 30. Let's check this. So let's apply 30 to this. Yes. Apply 30 to this. Yes. So in areas where you want it to be less dense, you can say specify, I don't know, 12. And you'll see that at the bottom. The reason we're doing this, well, okay, I applied at the top. But I mean, as you can see, they're spaced out a lot more. And the key to doing that, because of the limitations we have, and if you have a bigger structure, you don't want the entire structure to have millions upon millions upon millions of elements anyway. You know, that's a waste of computer power. You don't want to wait 2 days when you can only wait like 12 hours. You know, there's no reason to waste the time. So let's go back to 30. And then another method that you can do is the one-way bias. This is particularly helpful. The one thing to notice is that in your structure you now have arrows that denote direction. With this, you can, the one that I like to use is the L1 and L2, where you specify the distance between each node. And it goes by the endpoints. So in between, there's a progressive change between the distance of each node. So let's say L1 is going to be, L1 is the smallest one, let's say 0.05, or no, 0.1 is fine. And L2, let's say, is 0.6. The thing to remember with this, in this image right here, you've got a little arrow showing you that where the arrow begins, L1 is going to be the smallest. That's the smaller section. So when you look at your structure, the elements where the arrows are going down, when you click on it, you're going to have a much more concentrated meshing seeds up at top and less at the bottom. And then we can just apply it the same on the other side. Just switch it real quick. You can apply it to the sides. So that creates these mesh seeds. And one convenient thing about this then is when you end up going to create, or actually let's do on the, let's do over here, because whenever you have any kind of fillet or billet or some kind of curve, you want to take a little more time to make sure. In this example, it's not going to be too much of an issue because we're not applying any forces there or any type of stresses. But in cases where you are, it's definitely worthwhile to increase the count there. Let's do 40 on this. All right. So now when we go to create our mesh, solid mesh, select existing property. Be sure you select your property here. If you don't, you might end up getting really funky results or no results at all. You guys have talked about that, right? Creating properties? No? Are you going to talk about that later? Okay, so properties. So after you've created your geometry or imported it, and you've got it exactly how you want it, the next thing to do is properties. The properties basically tells you what kind of mechanical properties it is. So the steps to this are basically always just go for the isentropic or isotropic, and it's extremely straightforward. Let's give it a new name. Let's say mat2. And for input properties, this is where we're going to want to specify the elastic modulus and the Poisson ratio. Those are the only two you really need to specify, unless you plan on doing different or more advanced things. So with this, I don't know, let's say 2 to the 6th, I don't know, I'm just making stuff up. The one thing to be extremely careful with this is because Nastran Patran, like, it's unit independent. You need to watch all the units. You can plug whatever you want into this and it will give you numbers in the end. But it's up to you to decide or to be sure about the output. I know it was a huge issue last semester, and I know Nastran and Patran, they actually publish a little table online saying if you use these input values, these are going to be your output values for force, displacement, this, and this. So you can do it in either the SI or the imperial system. It really does not matter. So once you've got that, we don't need that. So once you've selected your material properties, you've given it a name, you can hit apply, now it exists here. Okay. What we can then do is we can click on the 3D properties for the solid. I don't know if you guys are doing 2D or 3D. 2? 4, yeah. So, I mean, you'd go to, in this example, you'd go to 3D solid, and again, you do the exact same thing. You'd give it some type of name here. For input properties, you'd click this, basically here's the material name. You'd click this little icon here, and we can then select our new material automatically. Whatever properties we gave, we can select that here. Just click OK. And we can select the application region. And in this case, we'd want to select the entire solid. We'd just click Add. OK. And then don't forget to hit apply. Oh, well, you got your name. Drop to apply. Okay, well, I already have it set up, but essentially what you do is you should not get an error if this is the first time you're doing it. It should just say, okay. And what it'll do, cancel. What it'll do is it'll show up in this little list here. And when you go to create your mesh, whatever name you've given here will show up as one of the input properties for the mesh. And that helps define, or it helps allow the program to essentially simulate or analyze whatever setup you have. Let me just delete that real quick. Oh. Okay, whatever. But that's it for the properties. It's really straightforward. There's really nothing much to it, except you need to get the elastic modulus and the Poisson ratio. Those are the important bits. So once you've gotten your mesh seeds down, the next step would be to actually create the mesh. In this case, I'm again doing solid. The basic parameters are fine. And this right here, this select existing property, this is where you'd select the property. In this case, the first property that I've already had in this is fine. You can create a new one down here, but you don't need to. Then you just hit apply. What have I done?
You did so.
Oh yeah, input list. So for the input list, you just need to select the solid. I know it can be sort of annoying because there's so many small individual input lists and so many, apply buttons. First you hit OK, then you hit apply, then you hit OK again, and then you hit this, that, and the other, and then finally it's right. But you have to be very, very careful because if you end up not, clicking the right button at the right time and the right point in the process, you're going to get an error, and you won't know why, and it's extremely frustrating. But now that you've got the solid selected and you hit apply, it should generate the mesh. As you can see, because of our mesh seeds, you have more elements near the top of the structure and more elements around the whatever surface or whatever kind of thing we're trying to include in our elements, say like a through hole or something. You've got that there. And at the base, there's not very many. And in this case, that's fine because we really don't care about the base all that much. There's really not much to it there. Now, I know one big issue is when you want to try to create a force somewhere that's not exactly, or that's exactly at a specific location. I know when you end up going to the loads, when you end up creating a force, if you ended up making a force, say, I don't know, force, input data. So let's say in the minus y direction, so minus 1,000, whatever. I have no idea what units I'm working in right now. I'm just plugging numbers in. But, I mean, what you can do is every number I've plugged in, if you just do SI, meters, and newtons, I mean, the resulting forces should then be in megapascals. So, okay. The key thing here is if you just go to regular apply the region, you can select either surfaces, points, edges, or entire solids. In this case, let's select a surface. If you click this, oh, nope, that's the solid. If you click on this top surface, say you want to only apply 1,000 Newton force at the very center point of it. Well, when you end up doing it this way, it actually applies it, what? Okay. What this does is it applies it at the corners. This is actually wrong. Your numbers will come out wrong and you will be very unhappy because your simulation will not make any sense. What this specifies, you're going to essentially be applying 4,000 newtons total. Well, 1,000 at different locations. I know that was a huge issue when you tried to compare the SolidWorks to this. In SolidWorks, they have a little more, it's a little more intuitive as to how you apply forces. But this would be wrong. You'd actually be applying way more than you wanted to. So the key with doing this is, and this is ridiculous in my opinion. I don't know why they do it this way. Let me just get rid of this. You actually go back to geometry, and you can again do this with whatever you import from SolidWorks. Select XY point, then you'd actually create point, method, we want to extract. Basically what this does is we can extract a point off some type of surface. And this is what we're going to end up needing to do. So the parametric position, this is essentially just a percentage. So if we want, let's say a little offset, 7. So let's say on the top. Oh. So now we've got, ignore the triangle, I created that earlier. So now there's a tiny little point here. I don't know how well you can see this point. Right here.
Change the background color to black.
Huh?
Change the background color to black.
This tiny little point right here. So we've extracted that point. But when you end up going to create your mesh, it's going to ignore that point. So we actually have to associate that point with our structure, our solid. So we'd actually go to, they have an action called associate, object point with a method curve, surface. So the point list is going to be this single point. Let's turn on. And the surface list is going to be the top surface. And when you hit apply, you now have an associated point. This point will be taken into account when you create your mesh. And if you want to apply a specific force at a specific location, when you go to create your forces or your loads, for the type, or for the force you create, the application region, you're going to want to select FEM. Oh, well, first we have to create the mesh again. I'm sorry. I'm sorry about that I'm jumping around. If there's any questions, please just ask them. So once you have the geometry, once you've got the points identified where you're going to eventually want to apply the forces, you want to create the mesh. The reason our mesh disappeared is because we had too many nodes in this. We're limited. So, that's why the mesh seeds are incredibly useful for this. Otherwise, just go wild and make, I don't know, millions. Delete mesh seeds. Create mesh seed. Forty. Okay. I'm just going to do a basic mesh. In whatever project you guys are doing, you're going to want to take way more care into identifying what parts are more important, what parts are less important, this, that, and the other, because depending on how strong or how powerful some of your computers are, it might take a little longer, it might go shorter. It's just all about how much time you have to spend on this. Okay. So, yep, we're under 5,000 nodes, so that's good. And it looks decently well for what we're trying to do here. So, the thing is, you want your mesh made before you go to apply your force, because you're going to apply that force to an FEM region. And that's important, because if you apply it to the point we made earlier, it's not going to register, you're going to get 0 deformation, 0 forces, and it's not going to work. So when we go to create our forces or our loads, and as you can see these blue arrows, have you talked about constraint forces?
No.
Constraints? Okay.
Yeah.
Yeah, so these are just constraints saying that it's not going to move anywhere down here. No translation or rotation. So when we go to create our force, just create force nodal, set the name, input data, it's still the same, minus 1,000. But for the application region, instead of geometry, we want to select FEM. And it's going to ask us to select a node. And this is where it comes in particular use. So we want to apply it to this node right here, the one that we created earlier. So that's node 3248, I believe. All right, let's add that. Hit OK. Hit apply. Now, when we zoom out, we're going to have a force that's applied at a single location. In this case, it's at offset because the initial one was centered, but that's no fun. So, all right, we got this. So the next step would be to run it. Oh, nope. So once you have your mesh done, you actually need to, so again, click the meshing tab, and in this little, sidebar again, go to action, equivalence, and you can pretty much leave every single setting here as it is by default. What this does is when you create your mesh, there's going to be overlapping nodes. They might be extremely close, but they're there, and they're going to be, it's just going to cause numerical errors when you end up trying to run your analysis. So what this does is, for every node, it checks within a certain tolerance, and in this case it's 0.005. If there's another node within that, it gets rid of that one, and it keeps the earlier one in the list. And this can actually reduce the node count. So not only does it make sure your results come out correctly, it actually allows you to run it a minute fraction faster. But it's extremely important to do so.
What tab is that under? Meshing guide.
Yeah, meshing, and then action equivalence. So then when we go to the analysis tab, I don't think I have any. No, good. So you want to, once you click the analysis tab on the action, we want to do analyze, entire model, full run. And down here with these subcases and subcase select, what you can do there is you can identify what specific things you want to test for. Generally, the default settings are just fine unless you have a specific, something specific you're looking for. But in your case, it should be fine. So you just hit apply. A little thing pops up. And it's going. It's done. After it's done, it should make a little beeping noise. You want to click on the XDB. What this does it basically ports all the results so that we can analyze it, so we can create plots from it. So again, access results, attach XDB, and all this is, again, it's perfectly fine just by default settings. All you have to do is hit apply. It looks like nothing happened, but when you go to the results, what you want to do is you can either click this button up here, the quick plot, the fringe and deformation, or you can just go to action, create, object, quick plot. And the select case results, this is going to be, you should only have one item here. This is the original analysis you ran. And when you look at the select fringe result, that's going to show you what exactly, like all the colorful stuff, like when you end up running an analysis, that's what we're going to want to look at. So in this case, let's look at the translational displacements. And for the deformation result that we're going to visually see that's going to deform the structure, let's just do translational displacements as well. And when we apply, we then get this, which shows us we actually have very little displacement on the bottom. And when you get closer and closer to where we applied our force, let's see if I can get the top down. You actually see that there are different regions that expand outward. Again, if you didn't do the force application on a single point, you're going to see the force application on the entire top, and it's not going to look right. You're not going to get good results from what you wanted. So that's always important to keep track of. And if you end up going to the constraint forces, this will then show you the forces that this structure is experiencing. So at the top, it's not, there's no force to oppose it. There's nothing stopping the deformation. But what's stopping the deformation, what's stopping the overall is down here where we put our constraints. So here we can see that there are internal forces within the structure due to the force that we applied and due to the constraints that we have. And I don't know, I'm trying to find, where do you have the, huh? Oh, no, not spectrum. Whatever. But, huh? The range bar for the colors.
Oh, double click the blue bar on top. Yeah, I just got.
Oh, okay, perfect. All right. So on the right, we can get an idea as to just what the magnitude is in some of the regions. Oh, and this brings up another good point. So when you increase the mesh count, theoretically, if you've set up your model correctly, you should converge to a single, you should converge to finite values. If you have your model set up improperly, you have bad geometry in your model, when you keep increasing the mesh count, the value balloons to infinity. So that's also important to take into consideration. And one of the huge things is when you have like a stress concentration point. So I don't have one in this case, but make one real quick. Actually, analysis. This. So say you have a structure that looks. Huh? Oh yeah. Hmm?
You said to my pieces.
No, I mean it increases, but I mean this is the force. You have to look at the displacement. But yeah, no, I mean, so what I was saying earlier is, if you have a right angle in your structure, you want to make sure that right angle is rounded. Any sharp point within your structure, that's going to be a point where the more nodes or elements that you have around that point, you're going to essentially balloon that value off to infinity. And this is only within, like on the outside, like if I didn't have these fillets up here, that's fine. That's not an issue. But if this inside here was a square instead of a cube instead of like a cylinder cut out, then those four corners inside the structure, those would need to be curved. And to do that, let me create solid cube length 1. Sure. No. Wait. I think it's not. Delete. No. Geometry. Nope. Transform. No. Oh, shit. Where is it? Oh, edit. Solid. Boolean. Oh, damn circle.
So I didn't talk to them about the Boolean operation, so you might want to mention what you were doing just there.
Okay. Actually, here. Okay, so are most of you creating the model in SolidWorks or this? SolidWorks? Yeah, so you really don't have to worry about this. You can generate the model in SolidWorks if that's easier for you. But for those of you that are doing it in this, it's really not that bad at all once you know where what is. I think that's the biggest thing. Let's do 6, 6, 0, 0, 9. So if you're creating any type of objects in this, oh, well, that was bad. Oh, here's the problem. Okay. So if you create any object in this, these little drop-down menus, they're extremely convoluted, but they're extremely useful. So say you have two structures, two solids. When you go to the action edit, solid, there's a method called Boolean. Basically what this does is you can remove parts of an object using another solid's geometry. So in this case, the target solid that we want to cut a hole into would be our larger object, and then the smaller one is the inside. Let me see if I can get that. What? 3. When you hit apply, we now only have, this is one solid now. There's no longer two separate ones. And this is what I was talking about before. If you mesh this up right now, these corners right here, you're going to get the stress values there are going to skyrocket the more and more nodes you put around it.
Can you show it as a shaded geometry? So the little green button in the bar. The little green button that makes it shaded. Sorry, little button below that and left. That guy, yeah. There. So you can see that there's a hole there now.
Yeah. So these four corners, we need to prepare them. Even if you're going to do an extremely minute fillet, like you need to add it. Not only does this like actually increase the mechanical strength. If you were to build this in real life, you'd increase the mechanical strength by doing this. So there's actually real reasons for doing it, but as far as the analysis goes, it's almost necessary. So the method to do this, again, we're going to be in the action edit. I'm working with solid. You can do, or no, we need curve on this one. I'm sorry. Where is it? No. Where is it? Add fillet. Here we go. So surface, add fillet. Now this is the tricky part in that, can we not do curve?
Yeah, solid. I think it's solid edge blend.
Is it?
Yeah.
Oh yeah, here we go. I'm sorry, yeah. So yeah, so edit solid edge blend. The easiest one is the one on the left. So basically you just define a single radius. In this case, I'll leave 0.25. It's relatively large for our model, but it should be just fine. Oh, what have I done?
Hit escape.
Here oh wow, okay, here we go. Let me get this right back. Okay. So you can keep auto execute on, off, doesn't matter. But what you want to do is you want to target this, whatever you want to add the fill to, that's what you want to click on. And it'll just automatically create the fill for you. Exactly how SolidWorks would do it, except maybe not as straightforward. So there we go. And again, even if you pick a very, very small fillet radius, you still need to add it. And then when we end up going to create our mesh, it's going to actually give us, it's going to converge to a value. And if you've ever used, yes?
I mean, let's pretend you work at a fillet in real life. Is there any way to relieve that stress at this real life?
Oh, yeah. It depends on It depends on how you, like what's around it. If you add something to stop, I don't know, if you're trying to stop bending stress or something. In most applications, there's certain limits. You know, you're never going to put 15 tons into the back of a, you know, F-150. So there are certain limits where you do have to say there's no way we're going to be able to strengthen this up much more.
Yeah, what I was more saying is there any way to get a more accurate FEA result?
Yeah, so
Oh,
in real life, you'll never not have a fillet. It might be microscopic, so you can just put something small there. As long as it's not 90 degrees, as long as it's something small, it should be fine.
yeah, like if you have anything welded, that's a real life fillet. But the smaller you make the radius, the more and more accurate it will be to, I guess, what you're trying to get to. But as far as the analysis goes, because this is still just a best approximation, you're never going to get actual, you know, 100% perfect real-world results. You might get close, but it's never going to be exact. So I guess the closest you can get is, you know, if you end up picking, let me see if we can. If we pick a very small radius for something, let's say 1. We apply it somewhere. I mean, it's almost, you almost can't even see it, but actually, yeah, you probably can't even see it there, but. Oh, no, what happened? It was just there. There it is. Oh my goodness. What am I doing? But I don't know if you saw it, but there was a fillet there. It was just extremely tiny. And even when it comes to doing the analysis, you'd still need that. If you're doing an internal, if you have an internal angle. In this case, where I applied it, it's useless. But it's still necessary for the analysis portion of it. I mean, the best results would be if you actually made it in real life and did it. That'd give you the most ideal results, but I don't know how much money you have to do that. But what else? Is there anything else? 40. Does anyone have any questions? Does anyone want to see anything done again? No?
Can you show how to do a boolean? Because I know that when I took it, we had to do a boolean where instead of cutting it out, we added more to the part. So like, can you do a boolean where you add something on side?
Yeah. Oh, that's useless, but okay.
No, that'd be good.
Edit.
So notice here that he's going to select one of the other options.
Well, yeah, I mean, there's 3. You can add, subtract, and if you want a complex shape that you can't readily make, you can also intersect. I know even in SolidWorks, if you want to make any type of rotor blades, impellers, the intersect function, even in SolidWorks, it makes creating those types of objects 1,000 times easier. I don't know who'd spend time to do it otherwise, but so select all solids, apply. Now you've got a dumb-looking solid like this. Yeah, and I mean you.
I mean, if you had it sticking out like that, you could put a force on it and see what happens.
Yeah, you could. Just maybe add a couple of fillets on the inside here, but.
Yeah.
Yep. I mean, if there's no more questions, yeah.
I know you did the one-way bias with the mesh sheets. Is there like a two-way bias?
Yeah. Create mesh seed. So you can have a two-way bias. So if you have, say, like a U shape, this would be exactly what you'd want to use. And again, you can do it with a ratio if you want a certain number and a certain ratio between the two. I just feel that's a little more complicated to keep straight. So I prefer to give exact distances and then let it just interpolate in between.
Assuming linear elements, what is the minimum number of elements through the thickness of the part that you need?
So that depends. It depends on what you're trying to get. I know you can model a lot of the three-dimensional stuff in 2D, but if you want to do a 3D analysis, I know you can select different. Let me see. Whoa. Great. Mesh. So in this case, we're doing tetrahedrals, and when they're constructed through this, in some sections it goes all the way through once. This is not a very big model, but I mean it really depends. One way you can find out if you need more is if you end up increasing the number of elements inside. We can't really do it with this program because of the limits we have, but if you increase the number of elements and you get a slightly like if it keeps converging on something, if the change in between each one keeps getting smaller, then at a certain point, I guess that's how you decide it. It's all relative, because I know if you do like molecular simulation, it's all relative to what you feel is good enough. I guess that's where you step in and say, well, there's no real benefit to adding any more. I personally don't know. I don't use Nastran Patran all too much, so I'm not sure.
Just as a ballpark value, one of my other professors for a different class said that if you're doing beam bending, that across the beam you have at least 20 elements as a bare minimum. And if your program lets you have more, then you definitely amp that up.
I mean, if you want to do, if you had this program and you had no limits on it, then I mean, you can pretty much do how many you want. But I know with,
Millions is typical.
I mean, in that case, I'd say you might get more accurate results with SolidWorks simply because we're paying for it. So, nothing else? Okay. That's it.